Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code graph problem, graph valid tree. Basically we are checking that whether the given graph is actually a tree or not. And this question has been asked in a bunch of different top tier companies, companies like LinkedIn, Google, Amazon, Bloomberg, Microsoft and Facebook. So these are my dream companies, so I'm paying my utmost attention. I hope you enjoy the video. Okay, so this is a LeetCode medium problem and we are given n number of nodes. We are also given a list of edges and we are told that these edges are actually undirected edges. Now we need to see that whether the given graph is actually a valid tree or not. If it is a valid tree, we'll return true. If it is not a valid tree, we'll return false. And we are also given an example to understand this problem. Like in this example, we are given these 5 nodes and we are given some list of edges. Based on this list of edges, they have shown that this could be a pictorial representation. And over here, they are saying that, yeah, this is a valid tree. So that's why they are returning true. Now the question is, in order to understand this, first of all, we will have to understand that what is the relationship between any graph and a tree. What is the difference between a graph and tree, and how can from the given input we can identify that okay, this is a valid tree or not, right? That every single tree is also a graph, but that is not the case for every single graph, that it will always be a tree, because if I put it in Venn diagram, essentially graph is actually a superset and tree is just one of its subset. So this can be a tree and this is a graph. There are a lot of lot of real life cases to understand that as well. Like the person who got slapped by Will Smith is always going to be a human, but not every single human has been slapped by Will Smith. It is something, that kind of relationship, right? Now the thing is, what are the differences between a graph and a tree? That inside the tree, all the components are connected, or all the nodes are connected. There is no restriction for graph that all the nodes should be connected. And the second difference is, inside any tree, we will never encounter any loops. So we can just say no loops. While inside the graph, there can be loops. Let's try to understand this with some examples. Is this a valid tree? Actually, yes, this is a valid tree, because notice over here that from one node, like every single nodes are connected with each other, and we do not find any single loops. But the thing is, say for example, in this case, if I had an additional edge, something like this, I can clearly see that there exists a loop between these 4 nodes. And because we have identified a loop, we can clearly say that this is a graph, but this is not a tree. Now let's take another example. Now this is a valid tree. Like all the nodes, they satisfy these 2 properties, that they are connected and there are no loops. The same graph, if I had some components like this, some additional nodes, though they are not connected with all the nodes, they are connected with each other, or there are some isolated nodes, something like this. If this is the case, this will always be true, that okay, this is a graph. We can put it in the category of graph, but this will not be a tree. And in this case, we will need to return false. Now, before we move on towards solution, I just have a simple request. If you see, a lot of people, they watch my content, but they are actually not subscribed to my channel. It takes me a lot of time and a lot of effort to make these kind of videos, and I would really appreciate if you can just show your support and subscribe the channel. Like, now this problem actually can be solved in so many different ways, and I'm going to show you few different ways on how we can do things. Now the question is, what we need to find basically we need to find that whatever this given input is this a valid tree or not. In order to find that whether it's a valid tree or not, we need to check 2 things: whether all the nodes are connected, and if there are any loops or not, right? So what I'm suggesting is that we break this problem in 2 parts. In the first part, we check that what could be the different ways we can see that whether these nodes they are connected or not. If they are all connected, we are good, and if they are not connected, we can return false immediately, that this is not a valid tree. And once that is done, we will find all the ways on which we can identify that whether there are any loops or not, right? So first, let's go with the first approach. Now our aim is to check that whether all the nodes are connected or not. What could be the different things we can do over here? In order to check that, essentially what we will need to do is we'll have to traverse over whatever this given input graph is. Now traversing over this given input graph based on the structure we are currently given in the input is going to be a little bit tricky, based using this number of nodes and edges. So the question is, like, first thing we need to do is we will need to convert this given input in either adjacency list or adjacency matrix. Either of them can be used and it will work perfectly fine, but in this case I will suggest to use adjacency list. We only use adjacency matrix when there are too many edges. We don't have any clear indication in this case that there would be too many edges, and we would try to use an adjacency list, right? So now we are trying to check that whether all the nodes are connected or not, and we have already created our adjacency list. Now what I'm suggesting is that through this adjacency list, we know that we would be able to iterate over this given input, and through this given input what we do is we create a hash set. Inside the hash set, initially it would be empty. Whenever we are at any point iterating over any single node inside this given hash set, we will check that whether that particular node already exists in the hash set or not. If it does not exist, we will add a new entry inside the hash set. And at the end, once we have traversed all the values inside the given input through this adjacency list, what we are going to do is we are going to check that what is the total size of hash set and what is the total number of n given. If both are same, we can conclude that from any single point we are able to reach to all the other elements, and because we were able to reach to all the other elements, all the elements are connected, and we at least satisfy one condition. So let's see that how it would work. Suppose in our adjacency list we start traversing through this position number 1, right? So initially we check that whether this value number 1 exists in the hash set or not. It does not exist, so we'll add an entry over here that okay, value number 1. Now through this value number 1 we can traverse in two directions. We can either traverse to the neighbor on the right or neighbor on the left. So let's say that we go to this node number 0, again we add 0. From this 0 we go to node number 2, again we come to 2. Now from this 2 we can't go any way forward, right? But the thing is we still need to go back. We'll need to do backtrack. We'll go back to 1, again through 1 we will go back to 3. Now at this 3 this is not added, so we add it over here. From this 3 we will go to 4, so we will add 4 over here. From this 4 again we will do a backtrack and we would come back at 3, and then we will come to 5, and then we will add 5 over here. Now at the end of this hash set we are able to iterate over all the elements inside the given input, right? And we check that what would be the size of this hash set. So size of this hash set would be 6. And what is the given n? So n is also 6, which means in this case we are at least able to conclude that this given hash set is actually satisfying our condition, and inside this given graph all the nodes are connected. So we are good. Now suppose in this case if we had another node, something like this, and this was not connected to any of them, basically this would not have been entered inside our hash set, and our n in this case would have actually been 7 rather than 6. So we can clearly see that if our size of our hash set is going to be lesser than whatever the number of n we have, if that was the case, we could have written false immediately, because we found that there exists some not connected component, and which was not the case in this case. So this is one of the very good approaches to identify that whether the graph is connected or not. Okay, now we have taken care of the first part, and now we need to take care of the second part, that we need to check that whether in the given graph does there exist a cycle or not. So first thing that comes to our mind is that why don't we use the visited hash set that we have already created. And in that visited hash set, what we are going to do is at any point in time, we are going to start exploring from one of the node in the given input graph. From that node, we are not going to stop exploring till we exhaust all the neighbors of this particular graph. And at every single time we are planning to come to next element, we would first check that whether that element exists in the visited hash set or not. If it exists, then we would consider that there exists a loop and we would break out of it. If it does not exist, we would add that entry over here. So first we will start traversing this value number 0. So it does not exist in visited, so we will add an entry over here. From this 0 we will start exploring its neighbor. So one of its neighbor is this value number 1, and remember that we are going in depth first search, so we will not stop until we exhaust all the possibility in one direction before going to the other neighbor. We could do it breadth first search way as well. It's up to us. Now from this one, again depth first search, we see its neighbor, that there is a neighbor 2, so we add an entry over here because it does not exist. Now remember that this is actually an undirected edge. So what does an undirected edge means? Undirected edge means that from 0 we have an edge to go towards 1, and from 1 we have an edge to go towards 0. Same goes from 1, that we have an edge to go towards 2, and from 2 we have an edge to go towards 1, and same goes from 2, that we can go to 0 and we can come back. Now over here from this position number 2, because we have an edge that goes to 0, we can consider that 0 is also a neighbor of 2. In this case, from this 2 we will try to go to this 0, and the moment we try to go to the 0, we will see that okay, it has already been visited, it is part of this hash set. So we would say that okay, there exists a cycle, and we are pretty happy with ourselves that hey, we have identified a cycle and now we are done with our case. But the thing is, this is actually a wrong approach, and the reason why it is a wrong approach, it is wrong approach because there exists this undirected edge. And let me show you by an example that what could be the problems if we keep using this visited hash set only, and how can we find false positives. So suppose we are given an example like this, that 0 calls 1 and 2, and that's it. This is the input we are given, right? And now we don't have any entry inside our hash map. Now the thing is, all the edges are undirected edges. Now because they are undirected edges, we can represent them in different manner. So let's represent them in slightly different manner. So from 0 we have an edge that goes towards 1, from 1 we have an edge that goes to 0. Same goes from 0 to 2 and 2 to 0. Now initially we start traversing from this 0. Now we have our algorithm that initially we are going to add the entry to visited hash set. So 0 does not exist, so we add the entry towards our visited hash set. Now from the 0 we need to check all of its neighbor before we move on to some other node. Now from this 0, first of all, let's say that we go down this path and we check its neighbor 2. Because there exists an edge like this, we are able to check its neighbor, right? So we are at this position number 2. Now at this position number 2, we don't have an entry in the visited hash set, so we enter an entry over here that this is 2. Now from this 2, again we will need to repeat the same process, that we will need to check for all the neighbors or all the edges that this 2 can point to. Now it does not have any edges that go further, but it has an edge that goes back to 0. Now the thing is, in this case, again we will use our same logic. So from this 2 we can still go to 0. So we will check that whether we have visited this element 0 or not, and over here we find that hey, we have already visited this element 0, which means by our logic that we were previously trying to impose, we could have said that okay, we have found a cycle that looks like 0 to 2 and 2 to back to 0, and we in this case say that hey, we have found a cycle and this is not a tree and we will need to return false and blah blah blah. The thing is, this is actually not the case, and why it's not the case is because of this correlation of having an undirected edge that is causing all this problem, which means that we cannot rely only on having a visited hash set. If we do that, then essentially we are not going to be able to find an answer, because in this case we know that from there does not exist an edge, and from this 2 we are coming back to 0 only because there exists an undirected edge from this 2 to 0, and that's why we can consider this 0 to be 2's neighbor. But in reality this 0 is actually parent of this child 1 and 2. So if that's the case, why are we still doing things like this? What could be a better approach we can use to find that what would be the solution to detect these cycles? There are a couple of different ways where you can tackle this problem. One way to tackle this problem is that initially, remember, the only reason we are causing this problem is because there exists an undirected edge, which means that there exist 2 directed edges from any 2 nodes. So what we can do is we can put a condition that from any point, if we travel from this 1 to 0 or 2, if we are able to travel in one direction, we would get rid of the remaining edge. And let's see that how it would work. So what I'm proposing is that initially we are at this 0th position. So we check in our visited hash set, we don't have any entry. So we add an entry over here that, okay, we are at the 0th position. Now from the 0, first let's say we travel to 1, which means that now we have traveled from 0 to 1 in this direction. So our aim is that we get rid of this reverse edge in our adjacency list. So if we get rid of that, now we are at this position number 1. At this position number 1, again, we add an entry over here in our visited hash set. Now from this position number 1, what we have to do is we will have to check that what are all the neighbors that we can travel to, or all the children we can travel to. But this one does not have any neighbor or children, so which means we don't have to worry about anything. So over here we can say that, okay, from this one we can't go anywhere, but thing is there still exists some nodes that we haven't traveled to, and we are using either BFS or DFS in any manner to traverse over entire graph, right? So which means that we will have to do a backtrack. So now from this one we do a backtrack. Now again we end up at this 0. But the thing is, in this scenario, remember, we are not ending up at this 0 because from 1 there existed an edge like this where we consider 0 to be 1's neighbor. We are coming back to this 1 because we are using backtracking through any BFS or DFS algorithm. We can implement this recursively or iteratively, doesn't matter. In any scenario we will have to iterate over all the nodes that are present inside the given graph, and since we haven't traveled all the nodes, that's why we are coming back to the 0. So again, this would be a new entry in the visited hash set. So again we come back at the 0, and this 0 we check that, okay, we have already explored one of the neighbor of the 0, but we still have to explore another neighbor. So again we repeat the same process. From the 0 we explored another neighbor of 0, we come back at 2, and immediately we get rid of this this edge that was coming back to it, and then we add an entry over here that, okay, we are at this position number 2. Now from this 2, again we don't have any more neighbors to go to, so now we have explored all the neighbors of 1, so we can mark 1 as being done. We have explored all the neighbors of 2, so we can mark 2 as being done. And now we come back at this 0, and we can mark 0 as being done because we have explored all the neighbors of 0 possible as well. And in any scenario we did not find any single loop because we did not find repeated value inside our visited hash set. So we can determine that there does not exist a cycle, and which means in this case we can return true because there are no cycles. So we can say that there is no loop for this one. And the only reason we are able to come up to this conclusion is because at every single position we were removing the edge where in one direction we have already traveled. So that is one way to take care of this problem, and the solution would work as expected as well, right? Now the thing is, there could be another solution where we can use the little bit different logic, little bit different data structure, and we can do things in better manner. And let's see that what would be that approach. So the second approach is that rather than using this visited hash set, we don't need to do anything with this visited hash set. Let it be used for the purpose of counting that whether all the elements are connected components or not. What I'm proposing is that we created another data structure, a hash map, and in this hash map, what we plan to do is we as a key we have parent, and as a child we as a value we have the value of its children. Now let's see that how can we use this combination to do things a little bit differently. Also over here, let's say that we are given a graph like this, that 0 1 2 3, something like this, right? So 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, and now we have this 3 connected back to this 1 as well, which means that there exists a cycle over here. Now because these are undirected edges, which means that they are bi-directional edges as well. So from this 0 we can go to 1, from this 1 we can go back to 0, and blah 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 whatnot. So initially let's say that we are at the 0th position. From the 0th position we start exploring its neighbor or children or whatever we want to call. So the moment from the 0 we are able to reach to this one, we would add an entry over here in this hash map, and the entry we are going to make is that 0 is actually a parent in this case, and one of the children that we could find for this 0 is actually node number 1. So node number 1 is the children of 0. And just stay with me that why we are using this approach. Now again, from this node number 1, we need to explore its neighbors, right? So what are the neighbors of this node number 1? We can explore neighbors based on the number of edges that goes out from this node number 1. So from this node number 1, we actually have 2 edges that goes out. First edge is that from this node number 1, we can go to node number 2. Now we check in this hash map that does node number 1 exist. Node number 1 does not exist as a key. So we add an entry over here. So we say that, okay, parent is node number 1, and from this node number 1, we can actually travel to node number 2. So we are good with that. Now again, from this node number 1, we still have possibility that we can go back to this node number 0. So again, we check in this hash map, okay, that whether there exists an entry for this node number 0 that we are trying to reach. Remember this very importantly. We will check that whether this node number 0 that we are trying to reach from this node number 1, does it exist in the hash map or not. Okay, so 0 exists in this hash map. Again, we check that from this 1 we are trying to reach to this 0, is this one of the children of this node 0 or not. In this case, yes, 1 is the children of node number 0. If that is the case, we can identify that this connection from 1 to 0 is actually not a cycle, it's just a trivial loop, and that is being caused because there exists an unidirectional edge on both the sides. So that's why we will ignore this case, we will ignore this connection. We are not removing the edge. Again, remember, we are not removing the edge, we are just ignoring this case, because in the hash map we are able to find that, okay, this 0 to 1 connection is actually just a trivial cycle, and we move on with our life. So from this 1, again, since we have reached to this 2, right, and 2 is not existing, and 2 is one of the children of 1. Now again, we are at this position number 2. Now again, from this position number 2, what are the different ways we can travel? We can either go back to 1 or we can go to 3. Let's say that we go to 3 first. So we check that whether 3 exists inside the hash map. 3 does not exist, which means we can create an entry that where 2 is a parent and 3 is a child. We are good with this so far. Now again, from this 2, when we try to check that from 2 we are trying to go back to 1, is that a cycle? So first we check that whether this 1 exists in the hash map or not. So 1 exists in the hash map over here, and 2 is one of its children. So because 2 is one of its children, we are going to ignore this case, and we are going to ignore. And because we are ignoring this particular, we are just going to move on with our lives. Now we are at this position number 3. From this 3, we will check that, okay, what are the different places we can travel back to. So from this 3, we see that, okay, one edge that goes to 1, one edge that goes to 2. First of all, let's explore this edge from 3 to 2. So over here, we will check that we are trying to reach to this node number 2. So 2 already exists, and 3 is one of its children, which means we are going to ignore this edge. So we don't have to worry about anything. Now again, from this 3, we check for this value number 1. So okay, from this 3, we try to see that whether we are able to reach to node number 1 or not. Node number 1 has already been visited inside the hash map, and that's why we are able to determine that there exists a loop inside over here, from where we are actually going back to one of the places that was actually not that is already been visited inside our hash map. And this hash map acts as both. It acts as a visited hash set that we were planning to use, and also it acts as a way for us to determining that whether we are detecting the correct cycles or we are detecting the trivial cycles between the unidirectional edges. And this would be a way on how we can check the cycles, which means that the combination of this, using this hash map to identify that whether cycle exists or not, and using this visited node and iterating over using BFS or DFS inside our graph, original graph, using these two data structures, we can actually get rid of both of our cases where we need to check that whether the graph is connected, and we need to check that whether the graph contains any cycles or not. And because we are able to do both of these things, at the end, if we are able to reach to end node, we will return true. If we are not able to reach to end node, we can return false. And this solution actually works perfectly fine. There are no issues with this solution. It is a very elegant solution. If you tell it in any interview, they are going to be very impressed with the depth and breadth of your thinking capabilities. What are the space and time complexity over here, and can we do something better? So let's first try to determine that. So space complexity, in this case, we know that we will have to use the hash map and we will have to use the visited array as well. Inside the hash map, we are going to iterate over all the nodes plus all the edges, which means that over here the space complexity would be big O of v plus e, because we are iterating over all the vertices and all the edges. The time complexity in this case would also be big O of v plus e, because we will have to iterate over every single node and every single edge multiple times in order to come to this solution. But the thing is, we are not doing loop inside loop work, so which means we are not doing repetitive work at any given moment. Okay, after such a long explanation, let's see that there be a better approach. And yes, there is actually a very elegant, very beautiful solution where actually we don't even have to go through all of these mess to detect that whether cycles exist or not. In order to do that, actually we need a higher knowledge of graph theory. What do I mean by that? Okay, at any given moment, suppose we are given a graph like this, that 0, 1, 2, 3, 4. Suppose we are given a graph like this, right? Now, if we want to identify that whether this is a tree or not, like in this case, we can clearly see that, yeah, this is a tree. There is a very legitimate scenario. There are no cycles. All the nodes are connected and blah, 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 whatnot. Everything is good with this, right? Can you notice an important property over here? The important property that I'm talking about is, if you count that what are the number of nodes and what are the number of edges, does there exist a correlation? Yes, actually there exists a correlation, and the correlation is that suppose we are given the number of nodes equal to n, and if we are given the edges that are n minus 1, and we determine that all nodes are connected. If we determine that all nodes are connected, because remember, in our solution, when we are trying to finding that whether the nodes are connected or not is much simpler. We simply need to use a hash set. We need to iterate over whatever the given input we have, and basically we can determine that, okay, whether the nodes are connected or not. But checking for the cycle is slightly more complicated, actually not slightly, much more complicated, because either we have two options and both options require us modifying a lot of things or managing a bunch of different data structures. Either we can choose to remove the edges like this, or we can choose to create a hash set like this. In both the cases, we are actually doing a lot of work. So what if we actually don't need to encounter that whether we need to find the cycles or not? If we only encounter that whether the given nodes are connected or not, if that is true, and at any given moment we identify that, okay, all the nodes are connected, and then we identify this property that whether the number of nodes that are given and number of edges that are given, if there is the difference between them is only 1, if that is the case, then the given graph will always be a tree. Let's see in this scenario. In this scenario, we can identify that, okay, from this 0, all the nodes are connected, that this 1, 2, 3 and this 4, we are able to connect to all of them, right? What is the number of nodes? So number of nodes in this scenario is actually 5. This 1, 2, 3, 4, 5. Now let's see that what are the number of edges. So if we calculate the number of edges, the number of edges is, okay, this is one edge, this is second edge, this third edge, and this is fourth edge. There are only 4 edges that are possible. If we have any more edges, then for sure there would be a loop. Because remember, where would you add an edge in this scenario? You can add an edge over here. Okay, that creates a loop. Let's say that you don't add an edge over here. Suppose you add an edge over here. Again, it creates a loop. Well, you don't even add an edge over here. You add an edge like this. So again, this creates a loop like this. Eventually, as long as the difference between the number of nodes and number of edges is actually not exactly 1, and if the number of nodes are one number higher than whatever the number of total edges are given, if that is the case, and we determine that all the nodes are connected, then we can clearly say that, okay, everything is good with our life and we don't have to worry about anything. Why we need to check that whether all the nodes are connected or not? The only reason we need to check if all the nodes are connected or not is, suppose we are given a scenario like this, that we are given these three nodes. Suppose we are given these 4 nodes, right? And in these 4 nodes, so remember our equation is that number of nodes and edges. So if nodes are 4 and if edges are 3, so we can say that okay, everything is good with our life. In this case the number of node is 0 1 2 3. Okay, so total four nodes, we are good. Number of edges 1 2 3, so this is also good. The thing is, over here you can see that there exists a cycle over here between these three edges. And why there exists a cycle? Because this particular node is not connected. So always at any case we will have to check that whether all the nodes are connected or not. And once we identify that all the nodes are connected, we are good, and then we can just wrap up our solution. So using this solution, actually everything becomes so smooth that if we calculate the time and space complexity, the time complexity in this case is actually big O of n, because we only need to iterate over the given number of nodes, and where n defines the number of nodes. If we calculate the space complexity is also big O of n, because we only need to maintain a hash set to take care of all the number of connected edges. So once we find out that what are the number of connected, if all the elements are connected, we can immediately identify that whether this given graph is a tree or not. So let's move on towards coding now. First of all, we are going to check that whether the given number of edges, if its length is one less than the number of nodes or not. If that is not the case, we can return false immediately. So, and if that doesn't happen, we will have to make an adjacency list. So we will create an adjacency list, so it becomes easier for us to iterate over the given input array. So for all the given n, we are going to treat them as vertices, and all the values that are provided in the edges, we are going to treat them as edges basically. Notice over here that for every single edge, we are actually adding 2 entries inside our adjacency list, and that is because the given edges are actually undirected. So that's why we will have to add an edge for both the nodes. So if there is an edge between 0 to 1, so we will have to create 2 edges, and those 2 edges would be 0 to 1, and from node 1 to 0. So that is what we are doing by this second for loop. Okay, now we will start iterating over the given graph inside the adjacency list. And I want to learn that how to iterate over the graph using stacks. So I'm going to do it using stacks, and I will be doing iterative depth first search. So first I'll initialize a stack of integer values and just name it as stack. And we will also have to create a hash set of integers called visited. Inside our stack, we will add the first entry. So we will add the node 0. And inside our hash map visited, we'll mark the first node as visited. We will pop the first node that is inside our stack, and then we will start iterating over its neighbors. And we'll see that if that neighbor has already been visited, then we will simply ignore that case. If that is not the case, we will start iterating, we'll start adding those neighbors to our stack as well. And we will also add that neighbor to our visited hash map as well. It would be neighbor, not node. Okay, and after this loop ends, we only need to check that what is the size of our hash set. So if, or else we will return false. And let's try to run the code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution works pretty efficiently.